Welcome to this problem walkthrough. In this session, we'll explore problem number 2219, titled Maximum Sum Score of Array. We'll break down the challenge, analyze the intuition behind potential solutions, and dive into the algorithmic approaches step by step. Let's get started. The problem asks us to calculate the maximum sum score of an array. Here's how this is defined. The sum score at any index in the array is determined by taking the maximum of two sums. The first is the prefix sum, which is the sum of all elements from the beginning of the array up to the current index. The second is the suffix sum, which is the sum of all elements from the current index to the end of the array. Our task is to find the index that provides the highest sum score and return that value. The input is a list of integers, and the output is a single integer representing the maximum sum score calculated for the array. Let's look at an example to understand this better. Consider the input array 4, 3, -2, 5, -1. For each index, we calculate the prefix sum and the suffix sum, and then take the maximum of those two values. At index 0, the prefix sum is 4, and the suffix sum, which includes all elements, is 9. The maximum is 9. At index 1, the prefix sum is 7, and the suffix sum is 5, so the maximum is 7. Similarly, at index 2, the maximum is 5, at index 3 it is 10, and at index 4 it is 9. Out of all these, the highest sum score is 10, which occurs at index 3. Now, let's consider another example with the array -3, -2, 0, -1. At index 0, the prefix sum is -3, and the suffix sum is -6, so the maximum is -3. At index 1, the prefix sum becomes -5, and the suffix sum is -3, so the maximum again is -3. For index 2, the prefix sum is still -5, but the suffix sum is -1, making the maximum -1. Finally, at index 3, the prefix sum is -6 and the suffix sum is -1, so the maximum stays -1. In this case, the maximum sum score is -1, which is achieved at both index 2 and index 3. This shows how the solution must handle negative numbers and still determine the least negative value as the result. There are a few important edge cases to consider. First, if the array contains only one element, the result is simply that element because the prefix and suffix sums are identical. Next, if all elements are negative, the solution must return the least negative value, as it represents the maximum sum score. For large arrays with up to 100,000 elements and values ranging from -100,000 to 100,000, the solution must be efficient and avoid exceeding time limits. Lastly, when the array contains a mix of positive and negative numbers, the algorithm should correctly calculate the prefix and suffix sums to determine the maximum score. These edge cases ensure the solution is robust and handles all possible inputs effectively. To approach this problem, we first consider the brute force method. The intuition here is straightforward. For every index in the array, we explicitly calculate the prefix sum by summing all the elements from the start of the array up to that index. As we compute these sums, we keep track of the maximum value encountered. While this method is simple to understand and implement, it involves nested iterations. Specifically, for each index, we loop through all preceding elements to compute the prefix sum, leading to a time complexity of n squared. This quadratic runtime becomes inefficient for large arrays, such as those with 100,000 elements, making this approach impractical for larger inputs. Additionally, it has a space complexity of 1, as it does not require any extra memory, but the inefficiency in computation outweighs this advantage. A more efficient solution is an optimized approach that leverages the concept of incremental prefix sums. Instead of recalculating sums for every index, we maintain a running total of elements as we iterate through the array. At each step, this running total represents the prefix sum at the current index. To implement this, we initialize two variables, one to store the current running sum and another to track the maximum sum encountered so far. As we process each element, we update the running sum and compare it with the current maximum, updating the maximum if the running sum is greater. This eliminates the need for nested loops and avoids redundant calculations. The result is a time complexity of n, as we traverse the array just once, and a space complexity of 1, since we only use two variables. This makes the approach highly efficient and well-suited for large input sizes. One alternative method involves pre-computing a prefix sum array. Here, we create an auxiliary array where each element stores the sum of all elements in the original array up to that index. For example, the value at index I in the prefix array is equal to the value at I1 plus the current element. Once this array is prepared, finding the maximum sum score becomes straightforward, as we simply iterate through the prefix array to find the largest value. While this method achieves the same optimal time complexity of O(n), due to the single-pass computation of the prefix array and the subsequent search for the maximum, it requires additional space proportional to the size of the input array. Specifically, the space complexity is O(n), because of the extra memory needed for the prefix array. This added memory usage can be a drawback, particularly when working with very large arrays. Among the approaches considered, the optimized approach using incremental prefix sums stands out as the preferred strategy. It combines simplicity, efficiency, and minimal memory usage. Unlike the brute force method, it avoids redundant calculations, and unlike the pre-computed prefix sum array approach, it does not require any additional space. This makes it especially advantageous in memory-constrained environments or competitive programming scenarios. The trade-offs are clear. While the brute force method is easy to implement, its O(n) squared time complexity renders it impractical for large inputs. The pre-computed prefix sum array is time efficient at O(n), but its O(n) space complexity can be a limitation. The optimized approach strikes the best balance, achieving O(n) time complexity and O(1) space complexity. The key insight enabling this efficiency is recognizing that prefix sums can be computed incrementally as a running total, eliminating the need for nested loops or auxiliary data structures. This makes the solution both elegant and robust for real-world applications. Here, we're tackling the problem of finding the maximum prefix sum of an array. A prefix sum at a given index represents the sum of all elements in the array from the start up to that index. Our goal is to determine the largest such prefix sum across all indices. To begin, we explore the brute force approach. The idea is straightforward. For each index, calculate the prefix sum directly by summing all elements from the start of the array up to that index, and track the maximum value encountered. To implement this, we initialize two key variables. The first, max_sum, is set to -infinity to correctly handle arrays with negative numbers. This variable will store the largest prefix sum we've seen so far. The second, current_sum, is used to compute the prefix sum for each index during the process. Now, we proceed with the brute force algorithm. We iterate through the array using an index variable, I, ranging from 0 to n1. For each index I, we explicitly calculate the prefix sum by summing all elements from nums 0 to nums I. To do this, we reset current_sum to 0 at the beginning of each outer loop iteration. Then, we use an inner loop to add each element from nums 0 to nums I to current_sum. After calculating the prefix sum for index I, we check if it exceeds the current value of max_sum. If it does, we update max_sum to hold the new maximum value. Once we've processed all indices, the max_sum variable will contain the maximum prefix sum, which we return as the result. To understand this better, let's walk through an example with the array nums equals 3, -1, 4, -2, 5. At the first step, where I equals 0, the prefix sum is simply nums 0, which equals 3. We update max_sum to 3 since it's larger than the initial value of -infinity. Next, for I equals 1, the prefix sum is nums 0 plus nums 1 equals 3 plus -1 equals 2. Here, the maximum remains 3 because 2 is smaller. At I equals 2, the prefix sum becomes nums 0 plus nums 1 plus nums 2 equals 3 plus -1 plus 4 equals 6, so we update max_sum to 6. For I equals 3, the sum is nums 0 plus nums 1 plus nums 2 plus nums 3 equals 3 plus -1 plus 4 plus -2 equals 4. Since 4 is less than the current maximum, max_sum remains 6. Finally, at I equals 4, the prefix sum reaches nums 0 plus nums 1 plus nums 2 plus nums 3 plus nums 4 equals 3 plus -1 plus 4 plus -2 plus 5 equals 9. We update max_sum to 9, which is the final result. Analyzing the complexity of this approach, we find that its time complexity is O(n squared). This is because for every index I, we calculate the prefix sum by summing all elements from nums 0 to nums I, which involves an inner loop. The total number of iterations across all indices is the sum of the first n integers, 1 plus 2 plus 3 plus n, which simplifies to n asterisk, n plus 1/2. On the other hand, the space complexity is O(1), because we only use a constant amount of extra space, specifically for the variables max_sum and current_sum. No additional data structures are required, making this a memory-efficient approach despite its computational inefficiency. This brute force method works because it explicitly calculates every possible prefix sum, ensuring correctness. However, it is inefficient due to redundant calculations, such as repeatedly summing overlapping parts of the array. To optimize, we can compute prefix sums incrementally rather than starting from scratch for each index. This leads to a more efficient linear time solution, which will be explored later. When considering edge cases, this algorithm handles them naturally. For an array of all negative numbers, the result will be the least negative number. With a single element array, the prefix sum is simply the element itself. For an empty array, the behavior depends on the problem definition, which may specify returning 0 or signaling an error. Notably, the brute force approach remains simple to implement, relying only on basic variables without requiring advanced data structures, though it struggles with large inputs due to its quadratic time complexity. This solution solves the problem of finding the maximum sum score of an array efficiently. The key idea is to consider both prefix sums and suffix sums as the problem allows choosing either side of the array. Here's the detailed explanation of the code. 1. Initialization. We start by calculating the total sum of the array, which helps in computing the suffix sums efficiently during the traversal. Additionally, we initialize two variables, prefix_sum to track the cumulative sum from the start, and max_score to store the maximum score encountered so far, initialized to -infinity. 2. Iterating through the array. Using a loop, we traverse each element in the array. For each element, we update the prefix_sum by adding the current element. We calculate the suffix_sum as the difference between the total sum and the prefix sum, adjusted to include the current element. We update max_score to be the maximum of its current value, the prefix_sum, and the suffix_sum. This ensures that we consider all possible scores at each step. 3. Returning the result. After processing all elements, the max_score contains the highest possible sum score, which we return as the result. This approach is efficient with a time complexity of O(n), as we only traverse the array once, and a space complexity of O(1), as we use only a few variables. It handles edge cases such as arrays with all negative numbers or a single element gracefully by considering both prefix and suffix sums at every step. Overall, this implementation is concise, efficient, and robust for the given problem constraints. Here, we start by importing the necessary Java utilities and defining the solution class. Within it, we create the method maximumSumScore, which accepts an integer array called nums. The first step in our implementation is to calculate the total sum of all elements in the array. This is done using a simple for each loop, where we iterate over each number in nums and keep adding it to the variable total sum. Next, we initialize two variables, prefix sum, which keeps track of the cumulative sum of elements as we traverse the array, and maxScore, which is initialized to the smallest possible long value to help us keep track of the maximum score encountered during our calculations. The main logic of the solution lies in the next for loop, where we iterate through each number in the array. At the start of each iteration, we update the prefix sum by adding the current element to it. We then compute the suffix sum, which represents the sum of elements from the current position to the end of the array. This is derived by subtracting the prefix sum from the total sum and adding the current element back to account for its inclusion in both the prefix and suffix sums. With the prefix and suffix sums calculated, the next step is to update the max score. To do this, we compare the maximum of prefix sum and suffix sum for the current element and then use this value to update max score if it's greater than the current maximum. This ensures that, as we traverse the array, we are always keeping track of the highest score possible. Finally, after completing the loop and evaluating all elements in the array, we return the max score as the result. This completes our Java implementation for finding the maximum sum score of an array. The solution is efficient, with a time complexity of O(n), as it involves a single pass through the array to calculate the sums and determine the maximum score. Let's start with example 1, where the array nums is 4, -1, 2, 1. First, we initialize three variables. The total underscore sum is the sum of all elements in the array, which is 4 plus, -1, plus 2 plus 1 equals 6. The prefix underscore sum is initialized to 0, and the max underscore score is set to -infinity because we want to track the maximum value as we iterate through the array. Now, as we move through the array element by element, we start with the first number, 4. Adding 4 to the prefix underscore sum gives us 4. Next, we calculate the suffix underscore sum, which represents the sum of the remaining elements after considering the prefix and the current element. For 4, the suffix underscore sum is calculated as total underscore sum prefix underscore sum plus number, which equals 6, 4 plus 4 equals 6. Now, we compare the current values of prefix underscore sum, suffix underscore sum, and max underscore score. The maximum among these is 6, so we update max underscore score to 6. Moving to the second number, -1, we add it to the prefix underscore sum, resulting in 3. The suffix underscore sum is recalculated as 2, and comparing prefix underscore sum, suffix underscore sum, and max underscore score, the maximum remains 6, so max underscore score stays unchanged. Next, for the third number, 2, the prefix underscore sum becomes 5, and the suffix underscore sum is 3. Again, the maximum remains 6. Finally, for the fourth number, 1. Adding 1 to the prefix underscore sum gives us 6. The suffix underscore sum for this step is calculated as 6, 6 plus 1 equals 1. At this point, we again update max underscore score by comparing it with the prefix underscore sum and suffix underscore sum. The maximum value remains 6, which is our result for this example. Now, let's look at example 2 with the array nums equals -3, -2, -1. Again, we start with the initialization. The total underscore sum is the sum of all elements in the array, which is -3 plus, -2 plus, -1 equals -6. The prefix underscore sum is set to 0, and max underscore score is initialized to -infinity. As we iterate through the array, we consider the first number, -3. Adding -3 to the prefix underscore sum results in -3. The suffix underscore sum is calculated as -6, -3, plus, -3, equals -6. Comparing the current values, the maximum is -3, so max underscore score is updated to -3. Next, for the second number, -2. Adding -2 to the prefix underscore sum results in -5. The suffix underscore sum is recalculated as -6, -5, plus, -2, equals -3. Comparing prefix underscore sum, suffix underscore sum, and max underscore score, the maximum remains -3, so max underscore score stays the same. Finally, for the third number, -1, adding it to the prefix underscore sum gives -6. The suffix underscore sum for this step is calculated as -6, -6, plus, -1, equals -1. Now, we compare all values again, and this time the maximum is -1, so max underscore score is updated to -1. This gives us the result for this example, which is -1. Finally, let's move to example 3, where the array nums contains only one element, 5. As usual, we start with the initialization. The total underscore sum is simply the value of the single element, which is 5. The prefix underscore sum is initialized to 0, and max underscore score is set to -infinity. With just one iteration in this case, we consider the only number, 5. Adding 5 to the prefix underscore sum gives us 5. The suffix underscore sum is calculated as total underscore sum prefix underscore sum plus number, which simplifies to 5, 5 plus 5 equals 5. Next, we compare prefix underscore sum, suffix underscore sum, and max underscore score. The maximum among these is 5, so we update max underscore score to 5. Since this is the only element in the array, the result for this example is 5. This concludes our walkthrough of the solution. By iterating through the array and calculating both the prefix and suffix sums at each step, we were able to efficiently determine the maximum sum score for each example. The time complexity of this solution is O(n), where n represents the number of elements in the array. First, the function calculates the total sum of the array using Python's built-in sum function. Since this operation requires iterating through the entire array, it contributes O(n) to the time complexity. Next, the function utilizes a for loop to traverse the array, during which multiple operations are performed. These include updating the prefix sum, which is a constant time operation, calculating the suffix sum using a single subtraction, also O(1), and comparing the current maximum score using the max function, which again takes O(1). Since these constant time operations are repeated once for each element in the array, the loop contributes another O(n). When we combine these, we get O(n) plus O(n), which simplifies to O(n), giving us an efficient linear time complexity for the algorithm. The space complexity of this solution is O(1), meaning it uses only a constant amount of additional memory regardless of the size of the input array. The function operates with three variables: total_sum, prefix_sum, and max_score. Each of these variables occupies a fixed amount of memory, so their contribution to space usage is constant. Additionally, the function performs all computations directly on the input array without creating any auxiliary data structures or temporary arrays. This ensures that no extra memory is allocated beyond the input itself. As a result, the space complexity remains constant at O(1), making this solution highly memory efficient. To understand how this solution compares to a brute force or naive approach, consider the following. A brute force approach would involve calculating the prefix sum and suffix sum for every possible split point in the array. For each split, this would require iterating through the respective subarrays, leading to a time complexity of O(n²). However, the space complexity would still remain O(1), since no additional memory is used. By contrast, the optimized approach in this solution avoids redundant computations by maintaining a running prefix sum and calculating the suffix sum in constant time during each iteration. This reduces the time complexity to O(n), a significant improvement over the O(n² of the brute force method. Importantly, while both approaches share the same space complexity of O(1), the optimized solution is far more efficient in terms of execution time. Now let's analyze the time complexity across different scenarios. In the best case, such as when all elements in the array are identical, the algorithm still needs to traverse the entire array to compute the prefix and suffix sums, resulting in O(n). In the average case, for any random input, the same operations are performed, so the time complexity remains O(n). Even in the worst case, for instance, when the array contains large positive and negative values, the algorithm still processes each element in a single pass, maintaining its O(n) time complexity. Mathematically, this is confirmed as the sum function iterates through the array once, contributing O(n), and the subsequent for loop iterates through the array once, with constant time operations inside the loop. Together, this yields O(n). As for space usage, the lack of additional data structures ensures that the space complexity stays O(1). Therefore, this solution is both time optimal and space efficient, with complexities of O(n) and O(1), respectively. When tackling this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases like empty arrays or arrays with only one element can either crash your program or lead to incorrect results. Always ensure your implementation accounts for these scenarios. Next, relying on a brute force approach to calculate prefix sums for every possible subarray can become highly inefficient for large inputs, often resulting in time limit exceeded errors. Instead, you should explore optimized methods like using a dedicated prefix sum array to reduce redundant computations. Another frequent mistake is incorrect initialization of the prefix sum array. For example, starting the cumulative sum at the wrong index, like beginning at index 1 instead of 0, can lead to subtle off-by-1 errors that are hard to debug. Finally, misunderstanding the problem constraints can trip you up. For instance, if the array contains negative numbers and you assume all values are positive, your solution might fail for certain test cases. Always read the problem statement carefully to avoid these pitfalls. Overcomplicating the optimized solution is another issue to avoid. Candidates sometimes introduce unnecessary complexity, such as adding extra loops or redundant calculations, which can negate the benefits of their optimization. Instead, aim for clean, efficient logic. Now, in interviews, problems involving prefix sums are quite common. Recognizing when to use this technique is critical. Watch for scenarios that involve cumulative sums, subarray problems, or difference arrays. Beyond recognition, interviewers will often expect you to evaluate the brute force approach first, identify its inefficiencies, and then propose an optimized solution. This demonstrates your ability to balance trade-offs effectively. Addressing edge cases is also important. Be proactive about discussing arrays with 0, 1, or all negative elements, as this signals thoroughness in your approach. Finally, be prepared to discuss spacetime trade-offs. For example, while storing a prefix sum array can improve time complexity, it requires additional space. Explaining how you weigh these considerations can leave a strong impression. This problem has connections to several related problems that are worth exploring. For example, in problem 53, maximum subarray, the goal is to find the largest sum of a contiguous subarray. While prefix sums can solve it, Cadan's algorithm is often more efficient and elegant. Problem 560, subarray sum equals k, leverages prefix sums combined with a hash map for fast subarray sum lookups. This approach is a great example of optimizing both time and space. Another related problem is problem 238, product of array except self, which uses a variation of prefix and suffix products to calculate the desired output without division. Finally, problem 724, find pivot index, requires computing prefix sums to identify a balance point where the sum of elements on the left equals the sum on the right. Reviewing these problems can deepen your understanding of how prefix sums and similar techniques apply across different scenarios. In addition to the prefix sum approach, there are alternative methods you can consider. Using a prefix sum array is a straightforward way to optimize subarray sum queries, as it allows you to calculate sums in constant time after an initial O(n) pre-processing step. The trade-off here is the additional O(n) space required to store the prefix sums. For specific problems like subarray sum equals k, a single-pass solution using a hash map can be more efficient. By storing prefix sums and their counts, you can perform quick lookups to check for matching subarrays. However, hash map operations can sometimes have unpredictable runtime, depending on the implementation. Lastly, the sliding window technique is another powerful tool, especially for problems involving fixed or variable-sized subarrays. It reduces time complexity to O(n) by maintaining a dynamic range of elements. The trade-off, though, is that it's only applicable when the problem permits adjusting window sizes without additional data structures. Understanding when to apply these approaches is key to solving array problems effectively. Great job making it to the end. To recap, we explored the problem, discussed a brute force approach, and highlighted key takeaways like the importance of optimizing with prefix sums. Thanks for watching. Don't forget to like, comment, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!